Okay, so a couple of ground rules just to remind everyone, even though you may have heard this a number of times. Torit will, unless Brian would prefer it otherwise, will hold questions until the end. And when you do ask questions, please remember to hit the touch pad on the microphone in front of you when you speak, because of course we are recording this live for our posterity. And this is also being viewed on the web, by the way, so there will be students and possibly others viewing it on the web. And let's see, what other ground rules do we have? That's it. That's about it. Okay, so I'm going to introduce you live. My mic's on. Your mic is on. Let's signal to the crew. Okay, and we are live. So we're very pleased to have Brian Lee with us today. Brian has a bachelor's degree in civil engineering from Northwestern University. And do you also have a master's from Northwestern?
Actually, I have my master's from Northwestern and my bachelor's at the University of British Columbia.
University of British Columbia. Okay. All the better. And he's getting his PhD right now at the University of Washington in Seattle, where he's been working closely with Professor Paul Waddell on the Urban Sim project. And he's going to share some of his research with us today. And he will actually be defending his dissertation within 30 days. So with that, take it away, Brian.
Great. Thank you very much, John. I'm going to assume that this is working, right? So the talk that I'm going to be giving today is going to be on accessibility and residential location choice. The title is a little bit long, so let me just give you an overview by breaking it down for you. And there are three main points. So there's the residential location part. I'll explain to you why that's important. But essentially, it's an anchor point for most people in terms of determining their travel behavior. And it's really important in terms of establishing the land use and transportation link. Accessibility, as defined as access to destinations and activities. There's been questions about whether it's still important in terms of determining residential location choice. So this research will has examined some of the literature, and then it's revisiting some of these issues with new twists and methods. And the approach that we're taking has a microanalytic approach, which basically means that we're doing things at a highly disaggregate level in different dimensions, and doing it in a way that's compatible with what's called activity-based type of modeling. And I'll explain that in a little bit. So overall, I'm going to place this presentation in the context of integrated modeling, the integrated land use and transportation modeling. For those of you who are not familiar with discrete choice modeling, I'm going to be just giving some basics about that so you'll understand the framework. I'll describe the application that we did in the Puget Sound region in the Seattle area, talk about the accessibility measures that were used, give some of the results, and then talk about some of the extensions into possible other applications and some of the other work that I'll be defending in a month. And then I should be leaving plenty of room for questions and answers at the end. So a lot of the audience here I know are in the civil engineering background. And traditionally, and very likely because of the way that infrastructure is tied in very much with what we think of as transportation, transportation as an area of study and practice has been developed quite a bit in the engineering context. And there are many goals, and one of the main goals in engineering traditionally has been safe and efficient movement of peoples and good. Now, it's a relatively narrow focus, but it's still a pretty daunting task if you think about the development of transportation. It involves designs of structure, geometrics, knowledge of different materials, especially when it comes to roads like pavement materials. And then there's also the management of the operations part, because there are a lot of moving parts, literally, with individual people acting all within the same system. And one of the tools that I'm going to be looking at is actually demand forecasting, because in a transportation system, we build infrastructure, but we build it in such a way that we kind of anticipate what the demand would be. So one of the tools for this area is travel demand models. And there are different purposes for these models, one of which is looking at evaluating the performance of the system. And it can be used for planning and policy purposes. So planning as relates to land use regulations, which traditionally has been in the domain of urban planning, and then looking at how these regulations and policy decisions get actually implemented, and the study of that has been in public policy or political science. The system, the transportation system that we're looking at, as I mentioned, we provide the supply, and that's relatively easy to measure because if you have a road, you know a certain amount of supply, but it's the demand part that's a little bit tricky. So in terms of the operations, what's in the most transportation agencies, we have these travel demand model, and the most common one is called the four-step model. You don't really have to know what the four-step model is, just that it's a way of figuring out how much demand there are by looking at what kind of trips people are taking for what purposes and what kind of mode they're using for wherever the destinations are and whatever routes that they're choosing. The main point of this that I want to take is that in traditional four-step modeling, the geography is usually zonal, so it's usually aggregate. It's trip-based, meaning that it's usually looking at where people go from a single destination to a single origin to a single destination, so that's one trip. And then the most important part that I'm going to dwell on is the fact that land use is considered as exogenous. It's usually considered as an input that's given, and there are certain problems with that. Some of the problems actually are that there's a feedback mechanism. Do you build a road and then there's development, or is there development and then that creates demand for travel? So there's a lot of feedback between land use and transportation that has not been traditionally recognized in transportation engineering. And we're actually seeing quite a bit of mental shifts, paradigm shifts, so to speak, from these more insular travel demand models to broader integrated land use and transportation models that will take into account these feedback loops and other types of complex interactions between land use, transportation, and public policy. By accounting for land use, we're better able to address a broader range of stakeholders and then the competing interests of those stakeholders as well as changing societal values. So we're no longer just looking at efficient movements of goods and people, but also looking at perhaps environmental sustainability, economic sustainability, and other goals that we deem that are important to us. And of course, when we're looking at both land use and transportation together, then we're better able to look at options for interventions. So instead of just questioning what should we build or how should we improve our transportation system, we could better look at where people live. For example, there's the urban growth boundaries that are in place in Portland and also in the Seattle area. Looking at those kind of regulations and what kind of effects there are between these land use matters and the transportation matters and really bringing the two together. And then other shifts are really looking at moving away from just a trip base and without really looking at specifically what kind of purposes people are using for travel into an activity-based environment where we're looking at why people are traveling, for what kind of activities they're doing, and then also disaggregating the geography, really dwelling down into away from the zonal environment and into parcels and buildings, and looking at agent-based behavior. So looking at individual behaviors, actors who are all part of the system that are contributing to how the system functions. So when we're talking about land use and transportation modeling, then there's not just the issues of what kind of trips takes place or where people are going and for what purposes. There are a lot of related travel decisions. That includes whether a household decides to own an automobile, what kind of employment, or whether an individual would be going to school. As a firm, as a company, you may be deciding where to locate your business, and as well as developers looking at where to develop their next project. And the one piece that I'm going to look at is the residential location, which I think is a pretty important in all of these pieces. As I mentioned before, most of us in our daily routines return home and start out at home in the beginning of the day. So it's a very important anchor point. It really determines where we're coming from and where we like to go at the end of the day. It's a big determinant of what kind of activities we can really access. And then residential location as a choice, we're really looking at different time scales. So each day you might get up in the morning and say, oh, it's a nice day, I want to take a ride on my bike, or so-and-so is going to pick me up in their vehicle. But residential location, we're really tying in the things that are down to the daily level in terms of our travel behaviors, all the way up to longer choices, including whether you own a car or not, and to what I think of, and even it could be longer choice of whether you are going to buy a home. So in that context, a lot of these questions can be looked at as discrete choice. So discrete versus continuous. Continuous could be how much milk do you want to put into a cereal bowl in the morning, or other types of things that you like to consume that's not so much neatly packaged up. Whereas a lot of these choices, you can really look at, okay, a household want to own 2 cars. Or in a primary residence case, you're really only choosing one or another place, but not really having anything in between. And with that said, I'm going to move on to describing a little bit about what discrete choice analysis is, the framework that we've used for this. Discrete choice theory has been largely developed by Daniel McFadden, who's at Berkeley and the winner of the 2000 Nobel Prize, and many others who contributed to this. And the basic tenet is that in terms of individuals' consumption habits, if we look at how individuals make those choices, then we're better able to look at the aggregate demand. So in terms of transportation, we can look at how many people are choosing to be on the road at a certain time, and then you can look at the system demand, or in this case, we can look at where people are choosing to live and how people are doing that to get a better understanding of some of the trade-offs between what people buy into their homes and their transportation options, which are affected by where they live. In discrete choice models, there are a number of assumptions, and I identify 4 main ones. That's who do you model the decision makers to be? It could be an individual, it could be a group of people like a household or a company. What the choices are, so the alternatives, so identifying what are among the things that people are choosing from, and then how to describe these alternatives. These are the things, a lot of characteristics that can go into factoring in people's decision making. So in terms of a home, definitely price is probably a pretty big one. Neighborhood characteristics, and then other things that you might want if you're a young person, you may want to live in a young neighborhood with a lot of things happening in nightlife. And those are the things that may not be as attractive to a retired person who's looking for a quieter type of life. And then given that we have those 3, then we really want to have some kind of decision rules that says this is how people make decisions. So the one that's commonly used is called random utility models, and I'll explain that in a second. But basically, if you see that the attributes, you could have a lot of different attributes, different scales, different measurements. What the utility model actually does is combine all those different things into one scalar number, one thing so that you can compare apples and oranges by their different characteristics. and is an ordinal type of comparison, so that you're really just saying that one thing is better than the other, but it's not any kind of absolute type of measurement. So random utility maximization, the basic tenet is that most people will, the actors, the decision makers will act rationally and pick the alternative that will give them the most pleasure, the greatest attractiveness of the alternative. So it's a probabilistic approach, and it basically says that the probability of someone choosing an alternative I is equal to the probability of that, the utility of that of I being the maximum of all the other alternatives. So the randomness comes from the utility function part, where the utility is really broken down into two components. The V part is the things that we know, things that we can observe. We can see that you've picked a certain place. We can see that this house costs so much, and we can see that it's so far away from certain types of activities that you might care about. And the random part is the things that we cannot observe, or things that we can observe, but the errors that are involved with those observations. So the error introduces randomness to the utility, and the way that you structure this randomness will affect the way that you can operationalize these models. And a very, very convenient way is to assume that it's distributed in a Gumbel distribution, which is very, very similar to a normal distribution, except that this distribution has certain qualities that allow for a mathematical form that's closed, meaning that we could write it out and we could manipulate it and relatively easily compute it. And it comes into this form that modelers would recognize quite easily. So this type of model is called multinomial logit model, which essentially means that there are multiple choices. And even if you're not mathematically inclined, that's basically all you have to know about it for us to move on. So for the residential location choice, there are lots of, we decided that the most logical way to model the decision makers are the households. And as far as the alternatives is concerned, there are different ways of you can aggregate these alternatives. You could do it in zones, which give you fewer numbers versus number of buildings or parcels. And in the lab that I work in Urban Sim, we've tried it in the beginning at grid cell level, superimposing some kind of grid cell on top. And now we're actually down to the buildings level, which is pretty similar to the units, because the majority of the buildings in a region are single-family homes. So as far as like apartment buildings are concerned, then we're not really telling that people are choosing a unit, but they're choosing among different apartment buildings. So this thing of picking out what the choice set is kind of important, because if you think about residential location choice, if we're at the building level or the unit level in an area like Seattle or Portland, we're really up to the hundreds of thousands and millions. So there are lots of trade-offs between how we model this. If we do it at a highly disaggregate level, then it may be computationally infeasible, and it's behaviorally unrealistic to think that people will actually look at every single building. But if you do it at a higher aggregate level, and you're really looking at neighborhoods and looking at averages of neighborhood characteristics, it gives you the computational efficiencies, but it may not allow you to look at specifically some of the trade-offs that people have to do between the residential choice and transportation. So what we've decided is to do it, model it at the building level. And we implemented the multinomial logit formulation. And the nice thing about a multinomial logit is that it allows for sampling of alternatives, meaning that instead, when we're modeling, instead of looking the entire set of buildings in terms of millions, we can still get consistent estimates of the coefficients for our equations from a subset of that universal set. So that's a very nice property that we're making use of. And so in terms of how we describe the attributes of the location choice, There are two main ways. We look at just the alternative variables themselves, so things like unit size, what kind of composition, and then different types of accessibility, but a common one that you can think of is, say, distance to the central business district. And then what we have on the other side is interaction variables, and that's primarily because in the multinomial logit formulation, we're looking at characteristics of the choices and seeing whether one is better than the other. And in order to incorporate the attributes of the decision makers, we need to have things that vary within the model. So a decision maker's attributes, the characteristics do not vary across the different choices that they have. So the way that they could contribute to this is by us interacting with the alternative attribute. So for example, the price of a home can be interacted by income by looking at disposable income, for example. If you decide to pay a certain amount monthly for rent and you have certain income, then your choices will vary depending on how much the price of that choice is. So one note is that if we were to be modeling this at an aggregate level, some of these characteristics would have to be averages or distributions, versus if we're looking at it at the building level, we can get specific values, allowing us to get a closer look at some of these trade-offs. So moving on to the application itself, it's, as I mentioned, in Seattle. I imagine a lot of you have been there. And the data sets, we looked at a lot of different census data, land use data, travel data from the Puget Sound Regional Council as well, and different types of geospatial data. But the heart of it is from a 2006 activity survey. This was a 2-day diary of activities and travel. It got about 4,700 households. And for this particular model, because we're looking at residential location choice, people who have made a decision about where they're moving to, we only took a subset of that sample, approximately 1,700 of people who recently moved in the survey. So there's a lot of interesting information in this last survey for the region. And one of the things that peeks out is not only do we have the current home information and the current work location, we also know where people lived previously. So that actually factors into the model a little bit. There's trip information, trip chains, and trip and tours. So trip, as I mentioned before, is just going from an origin to a destination. A trip chain is a number of trips that are linked together. So for example, a person's going from home to work, and then in the middle they go to a cafe to get coffee before. So that can be considered two separate trips, and then together they're a trip chain. And then a tour is essentially you're starting out from one origin and then ending up at the same origin. So at the end of the day, this person stops at the store and then come back to home, and then together this is one single tour. And so when we're looking at the tours, there are a lot of tour information in this survey. Primarily, over a third of them are still recognized as work tours, so work being the primary activity that these people did. And more than half of them at least made one kind of stop other than at work. So a lot of these people, well, half of them did something on their way to work or after. And as we can see, most of them did make a stop after. And the majority of these people did it for eating out or shopping or other types of consumer type of businesses. So just to summarize, we're using a discrete choice formulation for this and a multinomial logit framework. We're doing it at a household level, looking at building alternatives. And then the different attributes are like neighborhoods or building-specific qualities. And then for this particular research, where I'm looking at how accessibility affects people's decision in residential location choice, I looked at all sorts of different types of accessibilities. Now, accessibility is an important concept, and it's a pretty useful concept because it ties in pretty neatly land use and transportation. When we're defining it as the way that we can access activities, We're looking at the different locations, the distribution of activities in an area, and also the function and the extent of the transportation network, because the way that we go from one place to another is through the transportation network. Although this concept is pretty powerful and pretty simple, the measurements can be pretty complex, and it could vary a lot in terms of its complexity and the ability to actually capture some of these things. So I mentioned before that one simple accessibility measure might be just distance to downtown, but if you don't have anything to do with downtown and you don't have a need for that, it may not actually quantify your specific needs for activities the way that that measure captures. So in this line of research, there are a lot of unresolved issues. A lot of the previous research have really looked at work activities and households that have one workers. And so there's a prevailing trend of households with no workers or more than 2 workers. So what does that mean? What about non-work activities? There's a lot of changing societal values about work-life balance. So you want to be close to the mountains, you want to be close to shopping activities, you want to be close to, say, school. What about all these different things? And then what about trip chaining? So people are no longer just going from home to grocery store and then just coming home and then sit for a while and then do something else. With people's busy schedules, we're really trying to maximize what we can do. And looking at things from a trip-based point of view no longer serves that purpose. And finally, there's been some research that basically says that with the dispersion of activities, accessibility perhaps no longer matters as much in terms of where people live, because in places like Los Angeles, you could be in one area of the region and you could still access a lot of similar things that you can in other areas. So my research is really looking at, well, does it matter still? And if so, how? Accounting for some of these other unresolved issues like multiple workers or no worker households and trip chaining and non-work accessibility. So the accessibility measurements, we can basically slice this pie in a lot of different ways. The way that I'm going to describe it to you is general accessibility, which is only place-based. It means that we can measure it without any consideration of who's actually we're talking about. So the type of opportunities within walking distance of this building. So there might be a lot of things that you could measure, like restaurants, grocery stores, but let's say that you're a senior citizen and you really care about having a senior recreational center. That's not really perhaps going to be captured. Or if you're a young person looking for certain types of activities, nightlife, that may not be captured in here as well. And then there's the individual specific types of accessibility. Those take into account of the place characteristics, what we just talked about in general accessibility, but incorporating the person that is going to care about this. So, for example, in residential location of choice, if we're looking at specifically where people live and where people work, that travel time matters a lot more than, say, just the general travel time from a certain place to the central business district. For this research, I borrowed a concept from time geography. It's called time-space prism. This is something that was first described by Hagestad over close to 4 decades ago, and it's something that's been theorized a lot and even put into operations. The basic tenet of time-space prism is that you recognize time and space geography. The spatial aspect of transportation is pretty well developed, but some of the constraints as far as time concerned is not explicitly put into our models. So by explicitly recognizing time and space, it complements the activity-based type of models that we're moving towards, and it allows us to consider discretionary types of activities and trip chaining. So for example, instead of just looking at a trip from home to work, we're able to look at what kind of activities they can do in between, say, after work. And this is the specific example that I'm going to talk about. In this schematic, this plane is the geographic space, and then the vertical axis is time. So we have a person who starts out at home, and then travels to work, is at work until a certain time, T3, and then this person's off work. And then for whatever reason, this person has to be home by T4. Let's say that they have to, watch CSI or something, and they really want to be home. And so between that window, there are opportunities for this person to do certain things. In a more simplistic accessibility point of view, we may not be able to look at realistic choices that people can make given their schedules. In this case, if we're looking at their spatial constraint, which is their home and their work locations, the temporal constraint, which is this when they get off work and when they would like to be home, and also the transportation network, then we're really able to look at the feasible set of opportunities that this person can access. So in terms of application, we looked at this work to home trip chain, part of the tour, and we looked at the survey data of the departure and arrival times for everyone who made at least one stop after work, and then randomly assigned them to each of the workers in our model. And the measure looks at, given that we have this prism, we identify all the transportation zones that are feasible within based on those constraints and the travel speeds of the travel model. And then knowing that most people who make these kind of stops care about eating out, shopping types of activities, we accounted for the number of consumer types of jobs that are in this feasible zone. So this is really realistically the largest largest set of opportunities that these people can actually choose from. And so the modeling process is quite it's a sequential process where we have a base model only looking at control types of variables, the building neighborhood characteristics, all the other things that we think people care about in terms of choosing a residential location choice. And then I tried all sorts of different types of accessibility variables and ended up with 4 of them in the final model. And in this, I'll show you a sequence of variables that we incorporated into the model. The first 2 in blue are the general accessibility ones. These are only place-based. And then the last 2 are really individual specific. So we looked at the individual work travel time, specifically from the different home location alternatives to their workplace. And then the TSP, which is the time-space prism, looking at the discretionary non-work type of activities. So this is in your handout. It's a table that defines all the different explanatory variables. And then the second table shows in detail the model results. And what I'm actually going to do is going to look at a small part, which is just the bottom parts, the blue part at the accessibility measures. So the findings here gives us a lot of, confirms what we believe in. So compared to the base model, and each time as we add one more accessibility variable, we are getting what's called a log likelihood ratio. In terms of these kind of modeling, it's like a R square. And by doing a chi-square type of test, we're able to say that each of the following model rejects the preceding one. So what that means is that each variable is capturing something that the previous model did not capture. So as we move to the last column in Model 5 with all of the accessibility variables, we can see that all of them are statistically significant because of the t-values, and the coefficients reflects some of the tells us whether a variable makes sense or not. So the first 2 general accessibility variable and the shopping opportunities are positive, meaning that the more you have of something gives a person more utility, which makes sense. The more access you have to a different grocery store may make it a better choice. And then this one, the work travel time, is negative. And most people value time, so the more time that they have to spend traveling to work, having a negative utility makes intuitive and behavioral sense. So in addition to these modeling results, we looked at the relative influence of these variables. we basically wanted to see how much each of the variable contributes to the overall utility function. So in the interest of time, I'm just going to skip explaining this. And if you have questions and want to ask me about it later, I could do that. But move on to this figure, which is also on your handouts, which shows the different types of contribution of these utilities into the model. The last four are the accessibility measures, and by far the most important one is the work travel time accessibility measure. But given that we account for the general types of accessibility measures and the work type, we see that the consumer types of activities captured by this time-space prism still contributes quite a bit, meaning that non-work activities still matters in residential location choice. So what we conclude from this is that definitely accessibility still matters in terms of how people make residential location choice decisions, both work and discretionary types of activities. The time-space prism constraint approach has behavioral attractiveness to it. It's theoretically sound in terms of measuring accessibility, and it allowed us to capture more complex types of behaviors like trip chaining. And then the disaggregate approach, basically modeling down to the building level, we were able to, that helped contribute to capturing some of the possible omitted variables that weren't captured in previous model. And it's nice because it's also compatible with activity-based modeling and micro-simulation of this type of work. So I can move on to this if we still have time. I know it's 12:40. So shortly, I'm just going to talk about some of the extensions from this part to some of the work that I am finishing up now, and then some of the work that I would like to do in the future. Of course, with integrated land use and transportation modeling, there are lots of different travel choices that can be modeled. The modeling structure that we used here is it's something that's been used a lot, and there's room for improvement. And in terms of also the sampling procedure, we randomly sampled, and there could be better ways of sampling alternatives. So one thing that I'm looking at is the multinomial logit model. There are lots of pros and cons. I mentioned before that it's a closed and tractable mathematical form. It allows for random sampling. But one big con is the assumption of independence from irrelevant alternatives. And basically, this assumption says that each alternative does not have any shared relations and are independent from the other alternatives. So this doesn't allow us to look at some of the things that ties the different choices together. So if you're looking at housing choices, obviously, single-family homes will share certain characteristics that apartments do not. And then also looking at related choices, some of these things are not independent of other choices. So for example, in terms of residential location, there's the mobility question, whether you decide to move or not. Both mobility and location choice have been examined quite a bit individually and modeled as well. And the work that I've been working on is really looking at the connections between the two. And I've been in touch with other people who are working in discrete choice modeling, and we think there's a way to use what's called a nested logit model, which essentially is a more complex and more generalized form of the multinomial logit that we use here, to allow us to tie in these choices together and look at the connections between the two. And very simply, this is what it looks like. Without making any assumptions on the sequence of choices, the nested logit is just different level of choices so that we can structure the characteristics of the alternatives. On the top nest, we have a choice of whether someone moves or not. And then given that someone stays, which is on the left-hand side, then they're really staying at the current location. And then given that if they decide to move, then they will be choosing among a set of alternatives on the right side. The theory behind this is that when we make choices, we're not just making these choices out of a vacuum. Very often we're have some kind of reference point, and when you're moving from one place to another, the most immediate and the one reference point that most people will know the best is the current home where they live. You're going to be comparing oh, I have 1 bedroom and an office now, and look, I'm going to have 2 bedrooms coming up. This may mean more to you than someone who currently has a 3-bedroom and are downsizing to a 2-bedroom. So by putting these two choices together in a structure like this, we're better able to relate the current location of where people are living. So in the Puget Sound Regional Council data, there's information on where people were coming from, moving from their previous choice. And we're able to capture the relationships between the moving choice and the actual location choice. So I wanted to just finish off by acknowledging my advisor, Dr. Paul Waddell, and my lab mate, Li Ming Wang. And also we worked on this with Dr. Ram Pangela of Arizona State University. And here are some of the funding sources that we had for this. So without further ado, questions?
Please remember to hit the microphone.
Thank you. Could you let us know if how can we take into account the difference between work accessibility by a private car or transit? And did you take into account this? Or no?
So the measure that we used here was travel time to work by vehicle. And so I've tried different types of accessibility measures like travel time by transit, for example. The issue there is it's not easy to incorporate multiple accessibility measures because they are obviously correlated to a high degree, actually. So in a lot of places that are really centrally located, you may have really good auto accessibility and transit accessibility. And so those two a lot of times can't be in the model at the same time. So we tried it, but at the end of the day, we weren't able to incorporate it into this model. But I should mention that, for example, the second variable that we had was neighborhood opportunities for shopping, and that is a walking distance. So that should account for some of the neighborhood types of activities that people can access by walking within their residential environment.
Ali Zahir, you spoke earlier about things that now we should account about towards environmental sustainability, and I'm just wondering what have been done towards environmental sustainability.
In the bigger picture, this model, for example, in the bigger integrated land use and transportation system called UrbanSim, this model interacts with other models and allows us to look at, for example, air quality emissions. So, like I mentioned in the beginning of the motivation behind this, you could have different, a region can have different policies. You can choose to keep your urban growth boundary, or you could choose to relax them or make them more strict. Having these different things will affect the places where people can reside, which is taken into account in this model. And then given that we model how people, where they reside, and then that will affect their travel pattern. And then the travel pattern at the end will affect their accessibility and then also affect their residential location choice. So there's a feedback there, and then we're able to look at, how residential location choice, for example, can affect travel choices, which then affects like air quality from emissions.
Thank you.
Yeah.
Yeah, I'm curious to see if you use this model in British Columbia or Chicago or somewhere, and what the major differences are between Seattle, or what you anticipate the major differences to be between Seattle, and if they're still significant, et cetera.
Yeah, that's a good question because that talks about the generalizability of this model. We haven't applied this particular specification to any place else. The residential location model in UrbanSim has been applied in a lot of different places, and each place there are usually some distinguishing features that makes it unique. So, but in general, accessibility we know factors into these models, and they're always in some form or another. So I haven't done any comparison, but it would be kind of interesting to see if I can get my hands on these kind of data, perhaps even doing like a Portland and Seattle comparison.
We have a question from Helotes, Texas. How is land value incorporated into the model? Can your modeling methods be used to determine the change in value of similar physical structures with different accessibility?
Sure. So let me just go back to the table of the explanatory variable. So it's not explicit here, and this work is actually in a paper that's coming out where I've done some edits to this. But right here, disposable income is where land value comes into play. We looked at the price of a building, which includes the land value and the assessed value of the improvements that's on that land. And then we computed an annualized rent, so to speak, which accounts for the price of that building, which includes the land portion as well as whatever's on it. And then compare that, basically subtract that from the household's income to get at a disposable income variable. We worked actually pretty hard to get this variable in there because we know that price is really important. But price is also highly correlated with a lot of different things like size, the type of neighborhoods. So it's actually really difficult to get the price variable to have the correct sign and to be statistically significant. So this was one way that we were able to incorporate it, and we found that it actually works pretty well. So. John?
So I have a question for you. Earlier you talked about how to handle different types of households, those that have maybe multiple workers or those that have no worker in the space-time prism concept.
Right.
So how did you apply that here?
So that's not really... let's take the example of the multiple worker households. The accessibility measure using the time-space prism is at the individual level. So if you have 2 or more workers, then you'll have 2 or more measurements of the accessibility of those workers. And I tried different, and because the decision is actually at the household level, we're looking at a group of people that are together. So a household with more than 2, they have to somehow reconcile that difference and basically aggregate the individual accessibility measures up to the household level. I tried different things looking at combining those measures, summation, average. What I found worked best was really when I have more than 2 or more accessibility measures, I took the maximum value. And the interpretation from that, and for the travel time would be taking the minimum travel time value. And then the interpretation that we took from this is that the household is really trying to distribute across the different workers and not looking specifically at one or another worker's accessibility as being more important than the other.
Were there any limitations using the household survey, and are there other sources of data that you might be able to use this type of model with?
I think in general with this kind of modeling, the big limitation is the fact that this is still a cross-sectional study. So the Puget Sound region actually has what's called a panel data set, tracking people for an extended period of time, and there were 10 waves of them over a period of, I think, 12 or more years. By looking at a problem in a longitudinal sense, you can look at the development of the household, for example, incorporating life cycles, changes in life cycles that might cause people to change their preferences for different residential locations, the way that, the combining of households or the breaking up of households affect these decisions. So although in this survey we have the information for the previous location, and I should also actually mention that the second and the third variable, which is called same area type and same area, makes use of this information of the previous household location. What we know just from sifting through the data is that people generally move pretty close to where they are currently living, and most people like to live in similar types of areas. So if you're in rural Snohomish County, chances are good that you'll prefer to still stay in a more rural area. So this has some qualities beyond the cross-sectional aspect, but it's still really looking at a snapshot in time.
Yeah, I wonder if you could comment on, did you look at access to schools or education as part of the residential choice location?
Yeah, we're contemplating it. We know that some other people have in Washington State, there's something called a WASL, Washington Assessment School, something. It's a standardized testing, and some of those results are available, and they're by individual districts. So conceivably, you can attach that information and say that if you're in a neighborhood where the scores are good, then you may be able to assess whether the quality of school is good or not. We didn't do that here, and I'm not sure how well that kind of information captures. At the end of the day, we know definitely that school matters. Parents decide, to move to a special district just for their kids and for a specific period of time. But it wasn't incorporated here, and primarily we're brainstorming of all sorts of different things that we want, but we weren't able to find adequate data that we feel would reflect the school qualities.
I have maybe one broader question about the changing role of the concept of the work trip. That we all talk a lot about the work trip, and that's traditionally been what we focused on in these kinds of analyses. Do you see in the future that the dominant role of the work trip is going to change in all kinds of modeling, travel demand modeling or household location modeling? Because I meet people all the time who live in Portland, but their concept of work is in some other state, quite far from here.
Right. I think that's a very good question, and I think that researchers and practitioners too have been thinking about this for quite a while. There's a lot of research on telecommuting and whether we're going to just see these empty freeways with no one traveling to work in the morning anymore. That hasn't really materialized for a lot of different reasons, and there's a lot of psychology-related research on that. From what I see, I think work trips will still be important, whether we are caring about especially because we're moving more into a information and service type of economy. There are, restaurant workers will still have to get to restaurants. We still have to get to amenities. So we may be moving primarily away from the traditional concept of going to work in the morning and coming at home at night. But there might be still work trips that are related to you work from home 3 days a week, but you really have to have certain meetings at certain places. We still place a lot of value on face-to-face interaction. So I think that we'll still see more people doing telecommuting. If I had to bet, I would bet in that direction. But I think it'll still be important just because people who are providing the services will still be going to work and but having said that, as we move into activity-based type of modeling, we're really looking at work activities as well as all sorts of different types of activities. So hopefully we can not dwell too much on whether work is important or not, but look at work as well as all the other activities that sustains us all. Yeah.
I've read economic papers comparing urban growth boundaries to, I think what they call tolling regimes, where this is just a toll road system kind of throughout. And I guess I was wondering if there's just any data available, if there's any areas in the world where you could do this kind of discrete modeling and comparing those two factors.
So if I understand you correctly, the two interventions that you're talking about is tolling, some kind of tolling system, and then the some kind of urban growth boundary where you're containing the land use development, and whether there are any research opportunities or studies that have been done that compares the two and how well they work? Okay. I'm not aware of that kind of research that has been done. I know that certain places, like in Seoul, for example, they have a pretty contained, they essentially have a green belt around. And I know that researchers there are employing models such as UrbanSim and looking at different interventions, but I'm not aware of it. Seoul is the first one that popped into my mind because I know that they have certain types of tolling system and certain other policies that they have regarding public transit as well as the growth boundary. But that would be something that's kind of interesting to do. A colleague of mine did write a dissertation on tolling a specific piece of transportation network in the Puget Sound region, but I don't remember him doing specifically any kind of comparisons per se between, a strict land use type of regulations versus tolling.
So I just, is this particular model then going to be bundled in with UrbanSim itself, or?
So it's already, the model itself, the framework of the model is already in UrbanSim. And this particular specification, at least a form of it, is already in operations with the Puget Sound Regional Council. So we had to do some tweaks here and there, but essentially it is being used.
Okay, I guess that's all the time we have for today. Let's all thank our speaker, Brian Lee.
Thank you.
And I hope you'll join us next week. Professor Luca Quadrifoglio from Texas A&M University will be speaking about zoning strategy effect in ADA paratransit services, a simulation study from Los Angeles, California. So we'll see you then.
And if any of you students have questions that you've written down to submit, please hand them to Professor Bertini.